doesn't have that kind of objective reality. It's only relative to what you know. So if you're not measuring these photons that are being spontaneously scattered, then your knowledge is the trace over all possible ones. It's the mixed state. If you do measure, well, of course, you're going to get different information, and depending on what you measure, of course, you will have a different state of knowledge about the atom, conditioned on what you learned about the photons. But if you wanted to say, I am describing the whole thing, the atoms plus the photons, they are entangled with one another. And of course, depending upon what you measure on one part of an entangled state determines what you know about the other part. And it's not fair to say this or this happened. It didn't happen unless you measured it. Okay, so I think that's interesting. There was a lot of discussion about that 20 years ago when people were first developing this formalism. I think it's become much more of, I think, the general canon of knowledge now, how we think about open quantum systems, which is why I'm teaching it here. All right, now what we start to do, we want to move on a little bit to more general kinds of unravelings. In order to do that, we're introducing yet another piece of formalism here in the last week or so of class. Okay, some of it's somewhat heady, and we're not going to get too deep into it, but we're going to just at least touch on it. And this is formally writing our quantum trajectory as a stochastic differential equation. Okay, so this is just a formal tool of saying, okay, my state here evolves in a non-deterministic, non-linear way. And all the non-deterministic, non-linear bit is buried here at this particular stage. This is a so-called stochastic interval. It's an interval whose value is random and is picked from some probability distribution. Okay? And that probability distribution is dependent on the state of the system itself, which is why this thing is not linear. And it's an interesting fact that even though these individual quantum trajectories are nonlinear, the ensemble average is a linear equation on the density matrix. So all that nonlinearity washes out somehow in the ensemble average, but at the price of the fact that you're no longer talking about a state in that case, or a vector, I should say. You're talking about a density matrix. Okay. So this is the formula, this is what's known as a stochastic Schroeder equation. What we kind of showed very quickly is that if I look at, so if I write t plus ut as that if I look at the ensemble average, averaged over this probability distribution, that this is the Lindau measure. Okay. All right. Fine. So what I want to do now is, let's look at this. I'm going to keep this here, I guess, for now. Let's continue thinking about this unraveling, but let's do something a little bit more general than what I have written up here. Let's consider the case where I'm not just remixing the Krauss operators that are proportional to the jump operator, that's this guy. I'm going to mix this with this. I can do that. And I'll get the same master equation because it's the same CP map. So in particular, let's consider the case which seems weird to start, but will become physically clearer in a moment, where I'm going to define a new set of Krauss operators, and in fact, I'm going to have more of them. It's okay. You can have a CP map which has more Krauss operators. I mean, you can have more Krauss operators for the same CP map. You don't have to have, as long as you have these are orthogonal and rows and columns, let's define remix it. You can check that for yourself. And so I'm going to have the following form.
What do you mean by you can have more?
Well, I'll show you in a moment. It'll become clear. Let me just write this out now. That's what I mean. All right, so right. So these are two columns of a unitary matrix. They are orthogonal columns and orthogonal rows. Actually, only the columns in here, not the rows in that. And what you see here, I have now doubled, for every mu, I have two new Krauss operators. That's what I'm going to have more. So my Krauss operator, k mu, there are two, for every mu, I'm going to have two Krauss operators. It's going to be equal to this number, a mu, times the identity, plus or minus hold on a second.
You can just get rid of that 0 in that vector and it'll make tensorial sense. Because you have a 3 by 2 multiplying a 1 by 3 or a 3 by 1.
Sorry?
So your matrix there, is that 3 by 2?
It's a 3 by, it's a 3 by 2.
Yeah, and that vector is a 3 by 1. So you need it to be 2 by 1.
The vector should be 2 by 1.
The 0 is a part of the
You don't need that 0.
Yes, indeed. I'm sorry. Correct. Yes, indeed. Yes, thank you. But then it's good. Yeah. Right.
Is that supposed to be mod squared, the second row first entry?
This is not, indeed. Indeed, that is not. And in fact, I don't even want the half there. So, pardon me. Because now we add them together and square to order dt. This squared plus this squared to order dt is 1, which it must be because it's got to be a normalized vector. So now it's good. Okay. So this is equal to, and mu is equal to L mu dt. So this is equal to this. Okay. So these k mu, I have two new Krauss operators, and there are two new jump operators we'll call j mu, plus and minus. Okay. K mu, I mean k0, is equal to 1 minus a half a mu squared dt times the identity minus I over h bar h effective to order, to keeping things to the same order as v dt. Right? Plugging in for M0. That's behind it. This is H effective. And this is equal to the identity minus I H bar H effect, or H minus I H bar over 2 sum over mu and epsilon, J mu epsilon. Epsilon is plus or minus 1, J dagger J. So I have a new H effective. When you write J dagger J, you're going to get these A squares, and that gives you that term. Okay, just the same thing. So because we did this unitary remixing, we have the same master equation, but we have very different jump operators now. And in fact, Luke, you had asked the question last time, can you do a unitary remixing if you have only one jump operator? The answer is yes. Even if there was just one mu, I can mix M0 with M1, and I would have this form. Often, this you might call H effective tilde. It's a different H effective, but it's only off by a constant, and that doesn't make a difference in any of the now. You should always add anything to the zero of energy, and it doesn't affect. So we usually neglect this. All right, so we did some math, but what the heck are we talking about here? Well, and by the way, so alpha is, A here is a complex number. And it has the units such that A squared is a rate. Okay, it has units of 1 over time. So that A has units of 1 over the square root of time. So that this is dimensionless. And this is dimensionless. So what is this? Well, what these remember, every Krauss operator has an interpretation as coupling the system to an ancilla and then doing a measurement on the ancilla. In this case, we're coupling, well, we're generally thinking about our ancilla as the vacuum. Okay? And so let's consider, just as an example, suppose we consider the case of the damped simple harmonic oscillator. Where we just had one Krauss operator. And one Lindblad operator. The annihilation operator, right? Then, when our Krauss operators were of this form, when we had our n's, right, are equal to this, then the way we interpreted that was the following. We said that we have our, say, mode in the cavity, and we're detecting, by direct detection, the spontaneous decay out of the cavity. And we're going to see, in that case, a certain measurement record. In this case, we'll see some random clicks here corresponding to detecting these photons with an average rate, which is kappa times A dagger A. right? So, and then conditioned on this measurement record, I mean, we would see just a particular decay out of the cavity. So how else can we measure those photons? I mean, so this unraveling of the master equation with this choice of Krauss operators or Lindblad operators corresponded to direct photon counting. Sometimes we're measuring photons in the number basis. But how else can we measure the photons? Homodyne detection. That's another way we love. So in principle, I could, instead of taking those photons and directly detecting them, I can take whatever photon leaks out of this cavity and mix it on a beam splitter with a big local oscillator. And that local oscillator has some intensity. I'll call it or A squared, forget about mu. Okay, so this is the local oscillator's rate of photon that are being shined upon that beam splitter. Okay, and then we will get some kind of interference between the local oscillator and the spontaneously emitted photon, which we then can detect. Right? And what we'll detect in that case, the rate, instead of having this, the mode here is the interference between this mode, which has amplitude A, and this mode, which has this amplitude. So what we end up here with are new Krauss operators, J, or Lindblad operators, which are the interference between the local oscillator and the signal that is incident upon it, with a sign plus or minus that depends on whether I have reflection or transmission. That's what so we have a unitary matrix for reflection and transmission. Right? So, what these Krauss operators represent, and therefore these Lindblad operators represent, is homodyne detection. So that's interesting. We can, in principle, unravel the master equation by, instead of thinking about direct counts on the photon, we think about this kind of mixing. Of course, it's going to depend generally on the phase of the local oscillator. So we're going to get different information about the system, because whether or not if there's any kind of phase information about these photons, there'll be either constructive or destructive interference with the local oscillator, and that will affect. So what I'll see in this case is on one of those detectors is, instead of this kind of thing, under the condition that this is a large local oscillator, what I'm going to see as a function of time is some kind of signal like this with noise. I mean, God, it doesn't look like noise, it looks like one frequency. But my best attempt at noise. So, you get the point, okay? So this is my current that I see on one of these photodetectors. All right. Now, when I'm looking at a situation like this, I mean, it's true that, I mean, there's a whole bunch of photons, and this current that I'm seeing on this photodetector really is a bunch of discrete electrons. But once there are so many of them, it doesn't make sense to count every single photon that comes through. I should really think about the current within a certain time interval. Okay, let's explore that a little bit more.
Can I ask a question?
You can.
So before you erase me?
Oh.
Okay. So before you did this, it's okay. The remixing, there was one cross operator which was proportional to the identity, and
It's never proportional to the identity, it's
Yeah.
near identity.
yeah, it's near identity. But now all
And
of
there's-
them. So
Yeah.
are all of them near the identity now?
No, this one has this big factor out front.
Okay, so A is
A is huge.
Ah, okay. Yeah.
Mm-hmm.
Okay, and that's the difference between them.
Yep.
Okay.
So when you mix Lindblad operator with in not, which is unitary, right? Unitary like evolution. So that Lindblad will give you non-unitary like evolution.
You know, I think there's a lot of words that are being thrown around that aren't quite correct. The N0 Krauss operator corresponded to the part of the evolution conditioned on the null measurement, not seeing. And that wasn't unitary. It was non-unitary according to the effective Hamiltonian. It's just that that evolution was in the way that we described it, it was very weak. That is, in every time interval, the no jump didn't give us that much information. It only slightly updated the system in a non-unitary way, because it was close to the identity. Whereas the jumps, when we saw them, that was a whole bunch of information. And it really distinguished, in the case of the two-level atom, whether it was an excited or ground state. Okay? What we're doing now, as we are going to see, is making every measurement outcome a weak measurement. Because if I see clicks in this detector, it's really not, every click doesn't really tell me much, because it probably came from the local oscillator. It probably didn't come from the one photon that was emitted from the atom or the cavity. So the nature of this formalism is to enable us to examine what is the evolution of a system under the situation where there is both a Hamiltonian as well as a measurement. And both of those things are happening at the same time. The Hamiltonian is here, and the measurements are here and here. They're both in the M0 and in the MU, or the K0 and the K terms. And what we've done in this discussion to start is to say, well, we're going to try to analyze how we describe the evolution of the state of the cavity or of a two-level atom or what have you, when it's both undergoing its natural evolution according to its own Hamiltonian at the same time that we're continuously monitoring it. But in this case, we're going to continuously monitor it in a different way. And we're going to end up with a evolution that all measurement outcomes are kind of weak. And it becomes a more continuous stochastic evolution rather than one that involves these discontinuous jumps. And that's where we're headed.
So in this signal there is all possible measurement outcomes, right? Corresponding to k0 or to k mu plus minus at every instant of time, depending on the probability of happening. Or
Well, we have, yeah, exactly. We can write down this problem exactly as we did before, where we have the jump, no jump conditions. Okay, and in fact, if we wanted to ask, what is the probability that I have a jump in one of these detectors? If you like, a jump if it's the wrong word. I have a click in one of these detectors, right? Well, that's equal to that. And that, if we plug in, is equal to 1/2 a mu squared plus or minus a half a mu L mu e to the minus phi plus L mu dagger plus phi plus 1/2 all times dt. Where a mu has a phase. Okay? Because when you square this, you get cross terms. Okay? And of course, what this is a quadrature of that Lindblad operator. So this is, I'll call this x mu at that phi. Okay? So now we're going to, so this is, at every instant of time I can say jump, don't jump, jump, don't jump, jump, don't jump. However, if my intensity is sufficiently large, so I want to look at the case, I want to consider the situation in which the flux of photons from the local oscillator, or oscillators if I have multiple U's, is huge compared to the rate of decay, or whatever other, if there's a Rabi frequency or a detuning, anything else that's intrinsic to the dynamics of the system itself. Okay? Under that situation, firstly, this is negligible. Okay? That's sort of just the rate of flux of photons that are coming out of the detector itself. This term is going to dominate if I had the unbalanced homodyne detection. This is the whole story. But then I have this term, which is the interference between the quadrature of the system beaten with the local oscillator. So under that circumstance, what makes sense is to not ask at every differential time, jump, no jump. What you should do is coarse grain. And think about a time scale which is such that, so we're going to consider a time scale, coarse grain, such that delta t is tiny compared to 1 over kappa, okay, the rate of decay. but huge compared to the rate at which photons, or the time that photons are hitting my beam splitter. So that many photons from the local oscillator hit this thing before I have any chance of seeing those. And that's a typical case. We would work in a, you take a laser beam and you're looking at, say, the spontaneous photon. So under that situation, instead of asking jump, no jump, what I should say is in this time scale delta t, I have some stochastic number of photons that are incident upon these two detectors. Okay? And my update rule is then that conditioned on those detection events, I'm going to jump that number of times. This is the unnormalized form. So I don't just do one jump, I have a lot of them. Okay? All right, so let's expand that out. So, let's see. This is then equal to a mu over root 2 plus plus L mu to the power mu for the plus, and that for the minus. So now I'm going to factor out have a mu to the nu over root 2 all to that power. And then I have 1 plus L mu over a mu to the power n mu. So far, so good.
And we have only one mu in the problem?
No, in general, I have to sum over all mu. Although we never really considering those cases here, but in general, we would have many. Okay. Okay. If we're talking about the unnormalized form, we're going to renormalize anyway afterwards. There's no reason to keep this around. So we don't, because this is the unnormalized state anyway. Ultimately, we have to renormalize it. And then since this is huge compared to this, we can use the binomial expansion, put that in here. And so what we get when this is said and done is that the state unnormalized conditioned on, this is the no jump, I'm sorry, this is the jumps, this is this, we have the no jumps case still too, but the condition state conditioned on these sets of jumps is sum over mu 1 plus the lowest order in 1 over that big quantity. I also got rid of the DTs due to the fact that this is not normalized in the end anyway. All right? So, okay, fine. We have, we're at this point, this stochastic evolution depends on the stochastic value of this photon number difference between those two detectors. Okay? Now, what is that photon number difference? Well, we have it over here. So each one of these NUs, to start, we can think about it, this is a Poisson random variable. It has a mean value and a fluctuation around the mean. Oh, I guess I'm calling this delta here. Okay. And the mean value here, well, here it is. This is the mean value. That's what this probability is. So this is the mean value. We said the mean of those have probabilities. The fluctuations in this case are complete, in this short time interval delta t, are completely dominated by the local oscillator. Completely. So the fluctuations in this thing well, that's this equal to this by this, the square root of the mean. If it's Poisson. And that's then equal to the square root of mu squared over 2 delta t. Okay. Everything about the state of the system is here. The fluctuations are just the Poisson fluctuations from the local oscillator. All right, now if we assume that this really is a pretty big local oscillator with lots of photons, then we know that a Poisson distribution is well approximated by Gaussian. Okay? So when the mean number of photons is huge compared to 1, then we could use a central limit theorem to, instead of talking about Poisson noise, we say it's, to all intents and purposes, it's Gaussian. So if it's Gaussian, then we can write this in a different way, which is convenient. We say this random variable then is equal to the mean, but the fluctuation is Gaussian. It's Gaussian with that same, and so instead of having a Poisson random variable, which has this fluctuation, we have a Gaussian random variable, which has this fluctuation. And so we write this as follows. So delta W is, this thing is a stochastic Gaussian with mean 0 and variance delta t. Then it has the same statistics as this, except they're Gaussian. This is a Poisson, now we have a Gaussian. And such an interval such that the stochastic, is if delta W is a Gaussian variable, Gaussian random, with mean 0 and fluctuation, except for a given mu, sorry, mu and epsilon. This is known as a Wiener increment. So a Wiener increment is an increment whose value is random, picked from a Gaussian distribution, centered at 0, whose variance depends on the length of time you want that random variable to act upon. Okay? So delta W is kind of order square root of t, and that's important in all the stochastic calculus that we're going to talk about. We're not going to talk about a lot of it, because you got to keep things of order delta W squared, because they're of order delta t. So this is like diffusion, right? All right, well that's nice, because what that says then, let me just come over here to board number 3.
When you're doing post-grain approximation, it's already Gaussian, right?
What is?
When you're doing post-grain approximation?
Well, I mean, it only became Gaussian to the degree to which we had a strong local oscillator. If our I mean, you're right that they're interrelated. I couldn't coarse grain unless I had. I mean, I could have, but I would have missed some things if I. So they're interrelated approximations. All right. What was I saying here? Oh yeah. So what we need here is we're going to write this difference between the number of photons detected in one detector and the other as a stochastic variable. It's the difference of the means, and then plus the fluctuation in the difference. Okay? Square root. Because the noises add. They're independent noises. So this is equal to, if I look at the difference between these two, that's the balanced homodyne. That's mu times x. That's the difference in the photodetections. That's the balanced homodyne that appears here. And then this is equal to the square root of the sum of the squares of the two variances. The noises add. And that's then I guess I can just keep switching back and forth between capital delta and little delta. Hope you'll excuse me. I'm sure that's not the biggest infraction you've seen from me. Okay. And this is what I'm calling delta mu squared. Delta mu. This also has, this is another Wiener process which has the same variance. Okay. So the mean of delta W squared is delta T. Mean over all realizations, all possible, over the probability distribution. And I forgot this guy. These guys, so this is, so I have AU, I'm sorry, let me get it straight. Now this over root 2. That equals. Now it's got it right. Okay? So, what we have here is that the following. What we're looking at, this is the balanced homodyne. The balanced homodyne detection gives me the mean signal proportional to the quadrature plus Gaussian noise. So we have just, I mean, we could have written this down without going through all these steps if we just thought about it a little bit. What we're seeing is balanced homodyne. That's what we're conditioning our state on, that measurement record, and that measurement record is given by the mean signal plus Gaussian noise. And the Gaussian noise has a strength proportional to the signal, well, it's the square root, right? Because it's, and then fluctuations that are linear. So, with that said, we can just write that down over here, plug in for that balanced homodyne signal, which then equals So I just plugged in that balanced homodyne signal, and this phase came out there because we had a 1 over A, because the magnitude and the phase came up into the numerator. All right, very good. So, with that said, I can write down the full stochastic Schrodinger equation in unnormalized form, including now the non-Hermitian evolution associated with the no-jump possibility, and the x mu. Oh, I lost a delta t didn't I, over here. So this equation is of the same spirit that we described at the beginning of this lecture of a stochastic evolution conditioned on a measurement record, where that measurement record was, did I jump or did I not jump? Now my measurement record is conditioned, or my state is conditioned on the measurement record through this homodyne sigma. And that determines, this is in the unnormalized form. Normalizing it is a little bit of a pain. Should I do it? Do you want to see it? Do you care?
No.
No?
I mean, no, I don't want to see it.
Okay.
Probably the same thing with a bunch of factors in front of it.
Well, it's worth writing it down, but actually doing the normalization is a little bit of a tricky business. Because if I normalize the state, so if I want to ask what to normalize, so if I want to write down, I mean, I will write down what the final form is. The question was, did you want us to go through the steps to do it? Let me explain the point. Okay, we got to get that norm. That norm is related to the square, 1 over the square root of this inner product. Okay. Now when I take that inner product with itself, I got to be careful about the delta W squares because they become dt's. But you do all that, you take, it's there. It's not in the notes. I spent the whole flight going back from Atlanta trying to do it. I finally did it, but I won't show you because we don't have that much time. And I'm sure I made the people sitting next to me completely nauseous looking at these equations. But I will put these notes up on the thing. But I do want to give you this answer because we're going to get to one point of it that's particularly interesting. So when I do that, I get the following. So if I look at the differential equation, so now I'm going to write this as a differential. So my delta t's become dt's and my delta w's become dw's because that's how you always see it written. Equals the following. All right, so it's not particularly informative as you kind of suspected at this stage. It is the normalized form of this. So you could, if you wanted to simulate this on a computer, you could do it this way, but then every time you calculated your mean, you better normalize, because these expectation values are calculated with respect to the instantaneous state, which is normalized. Or you could do it this way, okay? Now, this form, one of the things, if, for example, we look at let's suppose, as we will see in the next lecture, I believe, if we finish that, a situation where the limit operator is actually a Hermitian operator. Okay? So let's suppose that L mu is Hermitian. Okay? And let's consider the case where the local oscillator phase, we're looking at the local oscillator phase, we'll call it 0. Doesn't really matter what it is. Then in that case, x mu is equal to twice L mu. Okay, or L mu. Is equal to a half x mu. Remember that we defined x mu somewhere. That's L mu dagger. Okay. All right, so if that's true, let's look at what this equation gives us. Under that situation, what I get is the following. d by the differential change in the state is then equal to minus I over h bar times the Hamiltonian minus 1/8 sum over mu x mu minus the mean x mu squared dt, or 8. And then I have minus a half x mu minus mean x mu dw, all acting on the state. That's interesting. This form of the equation is sometimes known as quantum state diffusion. Why? Well, it kind of looks like kind of Fokker-Planck-ish equation that we saw relative to a classical probability distribution with a drift term and a diffusion term. And what you see here is that the effect of the measurement is to try to damp out the state so that this gets to whatever its local mean is. And it diffuses it as well because of fluctuation-dissipation relation. They're kind of one and the same. And in fact, a solution, if the system were in an eigenstate of x, which remember is the measurement operator we're measuring, well, then this is 0, right? So what you can see, this kind of thing ends up, this quantum state diffusion will damp towards an eigenstate of x. And this kind of picture is one of the ways in which the whole, it was a completely different stream of thought in thinking about this kind of quantum trajectories. There was work by Percival and Gissen, the same Nicolas Gissen that many of you know these days from quantum optics, so this is back in, I don't know, the late 1980s, thinking about whether there was a way in which you can get a dynamical collapse of the wave function. That is to say, the state, through its interactions with the environment, dynamically collapsed to an eigenstate. Okay? And certainly, you can get such a situation if you measure the system continuously in such a way that you preserve those eigenstates. This is what's called, as we're going to discuss next lecture, a QND measurement. Now, one of the debates back in the day was whether, you know, the collapse of the wave function was happening objectively due to the interaction with the environment. The system was, that collapse was not a figment of our imagination, something that we did to update our state of knowledge, but, you know, the environment was pushing on the wave function and collapsing it, okay? I think the way we interpret it today is that this is just one possible unraveling of the master equation. This, again, if you were to do, it's not obvious, but if you do the statistical average of this over all possible trajectories, you get, again, the master equation. But if you don't actually measure anything, it's not fair to say that's what actually happened. It's just one of the possible real unravelings of the master equation consistent with the interaction with the environment. And if we don't actually collect those photons, it's not fair to say that that's the one that happened, because we have to average over all of those possible realizations. Now, I should say that actually what Percival and Gissen wrote down, I just want to conclude with one last point. So there was another point, but I'll say that next time. They actually didn't write down this form of the master equation that I just erased. They wrote down a slightly different form. Their form was this. So yet another unraveling. Here it is. This is a normalized, this is what's called the quantum diffusion equation in the literature. It's the one that Percival and Gissin derived in very different way. Now, what is this? It's the same kind of thing, except this is now a complex Wiener increment. It has a real and imaginary part such that the square of this thing average is ET. Complex guy. So what the heck? Where does this come from? This is another unraveling. And every unraveling corresponds to a potential measurement that I could have done on the system. And in this case, we're talking about something that's equivalent to measuring, we're thinking about the environment as the quantized electromagnetic field. So direct detection gave us the jump operators, the Poisson. The homodyne gave us the form we had before. Well, this is a trick question because we haven't talked about it. This is based on what's called heterodyne. There's homodyne and heterodyne. Let me just say one or two words about that before we quit. So, in all of the discussions that we have when we talked about continuous variables and all of the measurement, we imagined that we had some kind of signal that we wanted to measure, which was at some frequency omega. And then we had our local oscillator, which we assumed was at the same frequency, hence the name homo, the same. So when you have your local oscillator is at the same frequency as your signal, then there is a beat note which is at DC. Okay? So you see some current which has no frequency, no oscillation on top of it, and then whatever modulation on top of DC is the quadrature, for example. However, suppose that this is equal to something plus some delta omega, some detuning. Well, then you're going to get this, you're going to get beat notes. You're going to get, instead of DC, you're going to get what are called sidebands at the beat note frequencies, plus or minus the difference frequency. So what that means is that I'm going to have a signal that's oscillating. I'm going to have a cosine part and a sine part, which means that I have these two quadratures. I can measure effectively not just x or p, I can measure x and p at the same time. It comes at a price that if I measure one of these quadratures, one of these beat notes, I'm not measuring the other, and there's a kind of excess noise. It's a long story, which we don't have time to tell. But the bottom line of this is that instead of the signal being equal to x, the signal is equal to a. The complex, which has the real and imaginary parts associated with it, plus noise. So instead of measuring either x or p, I measure both x and p at the same time. That's heterodyne. And this corresponds to the same analysis we did, but instead of having the homodyne signal as conditioning, you have that heterodyne signal, and that leads to this. So if you ever see this, and I just refereed a paper, I was like, oh my God, we're still doing this? It's like, oh yeah, we're going to use the quantum diffusion equation to get up on trajectories, because years ago, Todd Brun and Rudiger Schatz wrote a library of these things that everyone can use, so it's convenient to try that out. Anyway, I think this is pretty cool stuff. What we're gonna do for our last finale, our finale lecture, is now ask the question, all right, fine, we have all these stochastic equations that correspond to different unravelings of the master equation when we don't measure the system, and then we average over them, we get the master equation. What if we actually do measure the environment in some way and study in more detail the way in which we can do this QND measurement to continuously collapse a system into an eigenstate, conditioned on the measurement record that we see. So we're going to talk about continuous measurement when we're actually doing the measurement. So, to be continued.